All right, thank you for your patience. And then let's start for, this is week 3, but the challenge set name is week 2. Yeah, so I firstly designed to finish everything in 1 week, but I realized that was too tough. And then it has been for a while to offering this class, but I forgot to change the challenge set name. So please regard week 2 as the challenge set 2, week 3 as a challenge set 3. Yeah. And then the reason why I released the week 2 challenges at week 2 was some of the students who were saying oh, I finished all the week 1 challenges and then give me some more fun. Yeah. So I released that, but yeah, please trust me. I do not wish to give burden to you. So it'll be the schedule is how can I put it so it was super difficult in 2018, but I accepted some of the feedback, and then it'll be smooth. So don't be afraid much about what will be out in coming weeks. Yeah. So one important thing is the week 1 challenge. Yeah, challenge set 1 due date has been passed. Yeah. So you can submit the flags afterwards, but yeah, the system will automatically get 50% of your score for those challenges submitted after the due date. Yeah, but yeah, and then so for we have a 1 week grace period, so you will still get 50% of points afterwards. Any questions for the week 1 challenge set submissions and others? And another thing is you might be curious about how your grade will be processed, but I will release the sum of the grading table on the grading website. So it's not prepared yet, but I will make sure to up on the website in this week. So basically you will get how much score you are earned, and then I will give a letter grade projection. So what that means is if you keep this amount of progress, then you will get letter grade B or A or something like that. Yeah, but that does not guarantee that you will get A. So if you finish all the challenges for week 1, they will say because it's just 100, 100, so you will see the letter grade A, but that doesn't mean that you can get A. So that just give some of the projections for that. Yeah. All right, so the objective for the week 2 challenges, yeah, are for we learned about the basic reverse engineering for week 1, but for week 2, we will focus on how we can exploit a buffer overflow vulnerability. Yeah. So now we know how to read assembly in the binary program. So we will utilize that knowledge a little bit to locate the buffer overflow vulnerability and take control over the program. Yeah. So the objectives are that we need to understand thoroughly about how the program stack works in both x86 and then AMD64. Yeah. And then here, I put the word ABI. How many of you have heard about the word ABI? So I bet you might heard about the API, right? Application Program Interface. So API is for human developers. So there is some of the program, and then we need to know how to interact with that kind of library or something. So it has a neat description about what kind of functions are available and then what kind of arguments we need to put. Yeah, that's API. And then ABI is for application binary interface, and that's not for human, that's for CPU. Yeah. So in the compilation process, we will the compiler will translate the source code into the binary format, but they need a certain rule that the CPU and then other the programs or other binary programs can interact with each other. Yeah. So it's not for human developers, but unfortunately, to get into that space and take control over it, we need to understand that. Yeah. But if you already finished it most of the week 1 challenges, then you will not feel much of difficulties in the understanding ABIs until week 4. Yeah. Starting from week 5, we will do something different. So yeah, at that time we will learn more about that. So the most important thing is we need to understand what is buffer overflow vulnerability, and then how we can exploit that to take control over the program, and we will learn about that. And to do that, so the most important thing is like we need to understand how the stack works. But from week 1 challenges, so either using like the by hand or using some of the tools such as Cutter or something else, we can identify. So if the program uses stack over access over EVP, but the negative index, that means it's the inside of the ESP and EVP area, so that these are local variables. And then some of the values putting above the EVP, that's out of your stack frame. So that's the arguments from coming from the caller. And then if the program accesses the stack using ESP with the positive index, but that's mostly putting the arguments to like the function that the current function will call. And this is the basic structure. So we need to focus on like the 0, 4, 8 for 32-bit, because 32-bit, their word width is 4 bytes. So that's why it increments to 0, 4, 8, C. 8 and C is like the C is 12. So in that way. So in 32-bit ABI, we can identify what kind of arguments that current function passes by positive indexing over ESP. But some of you might never seen like how that is done in 64-bit architecture. So interestingly, in AMD 64, we mostly do not use a stack to pass arguments. We use registers thanks to the AMD 64 architecture. In contrast to x86 only has 8 registers: EAX, BX, CX, DS, SIDI, BP, SP. Yeah, these 8 registers. But the AMD 64, on top of that, they have R8, 9, 10, 11, and then until 15. So it has like 16 general purpose registers. So we have 8 more temporary storage on CPU. So in AMD 64, if the number of the arguments are less than 6, less or equal to 6, then we pass all the arguments to the register and call the function. Then can you guess why we don't use stack to pass arguments on 64-bit? Yes. That's right. So stack is memory. Yeah. And then to put some of the data into the stack, it takes the travel to the CPU to MMU and then memory. And then if we directly access memory, it usually takes around 180 to 200 cycles in the CPU clocks. But in general, that does not take the too long time like that, because most of the stack contents that we will use is cached onto the CPU. But still, accessing to L1 cache means like that we need to wait until 3 to 4 cycles. And contrast, storing a byte to some data to the register only takes 1 cycle. So the only reason is like for the performance. Yeah, so the AMD 64 uses that. And then this architecture kind of thing is not new. So the x86 is quite distinctive for having like the very low number of the registers. So for example, ARM processors, they do have 32 registers from start. And then from the start that they always pass most of the arguments to the registers. Any questions for like this information? Yes.
If passing the registers is just better, why did we not do that for the 2-bit?
So in 32-bit architecture, we have like the 8 registers, and then we use 2 registers for maintaining stack, BP and SP. Yeah, and then so right now, like we don't use RSI and RDI in that way, but the SI is source and DI is destination. So they do have some of the meaning. And then we also use EAX to store the return value, so that we cannot arbitrarily use like all the 8 registers. Maybe we could use 2 to 3 registers, but we have many functions that has more arguments than that. But in 64-bit, we have a much more number of the registers, and that's why. Yeah. Yes.
Before x86, or are there other architectures that have more registries?
So it depends on the architecture. I'm not sure about like the more older architectures, but the Spark, yeah, it also has like the much more number of the registers than Intel. And then even for like the Z80 or like the very old machines like in 70s, yeah, they do have like a little bit of larger number of registers. Yeah. Yeah. Yeah, and then the main reason for having like the register, like lower number of the register is like it takes SRAM on CPU, so it's quite expensive. Yeah. So if we remove some of the registers, and then we can use that space with the transistors for implementing something else on the circuit. Yeah. So we call that in analogs to the real world, so real estate problem. So yeah, we need to keep like some of the space on the CPU to put many registers on it. Yeah. So same thing applies to the cache memory. So if we have a super big cache, then it'll be good. But the problem is like if we use that much space on CPU, then it will generate lots of heat. So we cannot increase the clock cycle or get the performance, high performance like the current CPUs. So for 32-bit, we will mainly focus on like those numbers to enumerate numbering like the order of the arguments. But in 64-bit, we have a specific order. So it's better to memorize it. Yeah. RDI, RSI, DX, CX, and R8 and R9. Yeah. So right now it might not be familiar to you, but maybe in week 5, and I believe like everybody will like automatically know that, and then yeah, you will naturally see like can order like the arguments in that way. Yeah. So the examples are so whenever you so let me tell you like some of the shortcut for the reverse engineering. Yeah. So in this class, I did not use like any kind of esoteric compilation, so reverse engineering might be easy. So easiest way to identify how the program calls a function and an argument is just identify where the call instruction is. And then near there will be some of the ESP access. Then we can easily identify this is a 0, 4, 8, first, second, third argument. Yeah. So the first argument is this one. Second argument comes from here, there. Yeah. So that's the thing. Then we can easily convert these instructions to the single function call like this. But I'm sure that you are somewhat familiar with this assembly, but for 64-bit, it looks like this. So this is a buffer overflow level 0 challenge, and then what it does is like from the EBP minus C and 8, it stores some of the integer value, and then it passes to the printf. And then these lines are doing the same thing. So in x86, to pass the first argument, we use the tag to pass it. But in 64-bit, we just put it on RDI. That's it. And then second argument, RSI, third argument, RDX, and then just call. Yeah. So you can see that like the 64-bit one is a much more simpler, and then because it does not use memory access, so it's a little bit faster. So first, second, third argument. So in 32-bit, focus on the numbers, attach it to the as a prefix to access to ESP. But in 64-bit, you need to memorize the order of the registers. So this is the order, but currently the order is this one, but it depends on the operating system too. So in Linux, AMD 64, we use like this kind of the calling convention, but that might be different in some other operating systems, for example, Windows and others. But in the most of like Unix POSIX systems, yeah, they would like to follow like the same calling convention. Yeah, so memorize a disorder for the calling convention for argument order, and for the others. So we pass arguments using registers in 64-bit, but to store local variables, we still use the stack because even for 64-bit, we do not have unlimited number of registers. So yeah, we need to put the local variables on the stack. So this diagram is very important. So whenever you are in the context of the running a function, you can always identify where the current stack frame is located in the memory. And then a stack frame is defined by the area between the ESP and EBP. And then in 64-bit, the register name is just changing as a E to R. So that might be RSP and RBP. So that defines a stack frame. And then another weird thing is like this stack grows downward. Yeah, we mostly learned that the stack grows upward as a stacking the plates on the dining hall or something. Yeah, but in this, like the how we use the computer's program stack, it's like it goes downward. So push means that the stack goes downward one block, and then pop means that like the stack will go up one block. Yeah. And then the ESP points to the end of the stack, and then EBP points to the bottom of the stack, but it's upside down. So this is the start of the stack, and this is the end of the stack. And then this can be nested. What that means is that, so if we call a function A, and then inside of function A, if we call function B, and then function C, then we can have like the function A's stack frame, and then if it calls another function B, then we will have a nested stack frame like this. And then function C, something like that. But so this kind of the stack frame is created whenever we call a function. Yeah, and then there must be something that we can remove this stack frame and go back to the original stack when the function returns. So we will see like how the function call create the new stack frame, and then how the return will remove the stack frame and then get back to the original one. And then important thing here is that the saved EBP, so that actually stores the stack frame of the parent function. So you can see the red arrow here. So the reason why I put it here is that in the stack frame, there's a saved EBP. I'm not sure you can see the characters here, but this is saved EBP. And then, so it will point to somewhere main's EBP, because suppose a main called a function A. Then if A calls the function B, then the B's stack frame will store the saved EBP as the parent stack frame. And then the reason why we record like that kind of the saved EBP is like whenever this function B returns, then we need to go back to this EBP ESP stack frame. Any questions? Yes. Pardon? Yes. So what we will do is like so whenever we remove the stack frame, we will just move ESP to EBP, and then move this EBP to previous EBP. So then we can maintain the thing. So we only need like the one value to maintain the stack frame.
But you not have to extend ESP to the stack.
So that is done by compiler. And then I have a few slides next, and then you will see that. Yes. Any other questions before we get into the assembly and then this kind of diagram and to take a look at that together? All right, let's move forward. So these assembly lines are some of the excerpted lines from like a buffer overflow level 0 challenge. And then in the main function, it calls receive input. Yeah, this is a call instruction. Yeah. Then let's start with the first question. Yeah. After finishing running this function, what instruction the CPU should run? So first we call the function and then return. Then what do we expect the CPU should run afterwards. So this instruction, yeah, maybe the answer is too straightforward. So yeah, so after calling this function, we are expecting that the CPU must run this instruction. So, but how CPU runs is like the CPU only has a one focus. Yeah, if we call the function, then their focus will move to that function, and then they don't know about what they are running. So that we need to keep track of the state and then guide them to where they should get to. They should get back. So whenever Intel processor emits a call instruction, what it does is internally, so you can think the semantics of the call instruction is push EIP. So push the instruction pointer and then jump to the target function. And then here, so if you try to take a look at the specifications and then assemblies, then in Intel x86, you can never access the register EIP. So EIP is a virtual register to like the us, but the CPU internally maintains that. And then what EIP should point is the next instruction the CPU will run. So when we run the call instruction, then EIP will automatically point to the next instruction. Yeah. So in that case, in running the call instruction, we push EIP. That means, so the current ESP is at here, and we will store the next instruction address as a return address on the stack. This is how we will let the CPU, to where to go back when the the target function returns. Yeah. And then the CPU will move to that receive input function and just run. And then here, these 4 lines are from the receive input. So after the call receive input, it will store the return address as the next instruction that it will run, and then move to this function. And then in every function, they do have like a so-called function prologue. And then what these lines are doing is like manage to create the new stack frame by manipulating the EVP and ESP. Yeah. So suppose before, so let's take a look at the before calling the receive input. So EVP and ESP points to the stack frame of the main. Yeah. And then when we call the function, we will just push ESP to store the return address. And then starting from here, we will create a new stack frame. And then it starts with push EVP. Yeah. So not just for storing the return address, we also store the EVP value where the parent function's EVP should be. Because whenever the function returns, we will restore the stack frame too. And to do that, we need to store EVP like this. And then the next instruction is that we will set EVP to be the same value as in ESP. And then this is okay because we stored previous EVP value. So we know how to get back. So we can override that. And then it has a weird instruction called the push ESI. But sometimes there is a push ESI or push EBX, or sometimes there are not. But the reason why it stores the ESI is like internally, this function will modify the value of ESI. But the upper level function might have stored some important value on ESI. Then if the child function overrides that, then the program might be inconsistent. So that's why we store ESI on the stack too. So the important thing here is that whenever we need to modify some of the registers that the upper level function might have used, then we need to store those kind of value on the stack, and then we need to restore them all before returning to the upper level context. And then one of the question was like how can we manage the ESP, right? So we just get down EVP to the previous ESP, and then the new ESP value will be defined by the compiler. And then when the compiler compiles a function, they know that how many of the local variables are, what is the size of the buffer, and also how many of the argument space is required for their colleagues. Yeah. So specifically for this receive input, compiler determined that they need like the 84 bytes. So 0x54 in hexadecimal is 84 in decimal. So it subtract 0x54 from ESP, so it reserves a new stack frame. And then that's how we create a new stack frame whenever there's a function call. Any questions about creating the new stack frame? All right, then let's move to next. And then this is the internals of the receive input function. And then internally, it prints out something and then asks you to like give some, you get some input, and then you can run it. And after that, how it works is that, so the receive input function uses three local variables. Two variables are integer, and then one variable is a buffer. And then for, wait a second. Yeah, right. So for the local variables, we will use the EVP and then negative indexing. So we will store the local variable near the EVP. And then we will put the argument to pass to the callee near ESP. And that's how we use the stack. And then from these kind of the instructions, we can identify that the EVP -8. So you can regard each block is 4 bytes. The -8 is here, so we store this value, and then -0c -12 is it here? Yeah, and so on. And then when you get to the point that like you will pass the argument, then you can identify that EAX comes from here, so you know that the first argument is this one, but the second argument is coming from ECX, that's from EVP -8, so we can see that the value is here, and then so on. So this is how the program uses a stack frame to pass the argument to the callee. And then there is a call instruction too. Then what was the semantic of the call instruction? Push EIP and then jump, right? So it will push return address. But when we are running this call instruction, EIP is pointing to the next instruction. Yeah. So call this address will automatically store the next instruction's address as a return address, and then get into the printf. So then this is what printf will see. And this is actually very similar to what we have seen before calling the input function like this. So in this case, we don't have any arguments to the receive input, so I omitted all the arguments. So return address, and then ESP is pointing to the return address. That's what the function start expects. And then that's actually same for calling the printf. These are argument, and then there's a return address, and then ESP will be right at that point. Yeah. So this is an invariant for calling and returning the functions. And then if we keep this, then we can call many functions nested and then returns, then like all the state will be maintained correctly. And then let's take a look at how the function returns. So these 4 instructions ending with the return. So at the end of the functions, you will see the function epilogue. So we learned about the function prologue for the how we create a stack frame, and then these instructions are function epilogue. And then the compiler also knows that the how many bytes it will use for the stack for a function. So the same number 50x54. So when we need to return to the upper level stack frame, so we need to restore this ESP by adding the same value that we subtract before, then it will move up to here. Then previously, before subtracting ESP, we pushed ESI. So the next instruction is a pop ESI to restore the ESI value to the what previous function expects. So this is the state after executing the pop ESI, and then our current ESP points to the saved EBP. So we also need to restore the EBP value. So we will run pop EBP. Then it will move up to the previous stack frame. Yeah. And then return is the semantic of the return is pop EIP. Yeah. Pop and then just move to there and then run it. So pop EIP. Then take a look at the location of the ESP. So it's right above the return address. So like they will point to this white area. Then let's take a look at the stack frame that we are running before running the call instruction. So the state is exactly the same. So that we don't care about what kind of values or garbages are remaining here. So just focus on all the values above. Yeah. And then the ESP and EBP values. Yeah. These are all restored correctly. Yeah. This is how function call and return works. Yeah. So any questions about how we can nest the stack frame and then return? So every time you got confused about the how stack works, yeah. So please try to draw this kind of the diagram. Yeah, then that might be very helpful for understanding how it works. And then I'm a bad drawer, and then if you're if you're not that good at drawing the thing, then we also have a GDB debugger. Then GDB debugger will print out not beautifully like this, but at least they will show all the values. Yeah. So if you can match this kind of diagram and then GDB debugger and those kind of values, then you can imagine how it works. And that's very important for the writing exploitation, because in the most of cases, if you make any kind of mistake in a bit or something, then it will never work. Yeah. So that's why. Then let's move on to the buffer overflow vulnerability. So this is the actual source code of the buffer overflow level 0 challenge. I know that the source code is not available, but yeah, if you do the reverse engineering, you can easily get this kind of the output. Yeah. And then the vulnerability that the buffer overflow is happens when we put more data than a buffer can store. And then here the character array buff is size as 20, but at the end it runs fgets buff, and then it reads input from the user up to 128 bytes. So it will get 108 bytes more than it can store. Yeah, this is the condition of the buffer overflow. And then when the buffer overflow happens, most of cases, what you will see is a segmentation fault and then just crash. But we will learn how we can control that, and we can run whatever we want. So let's take a look at that. And then although the buffer size is 20, to simplify the diagram, suppose we have a buffer size is 4, and then that does not affect to the understanding the concept much. Yeah. And then if you take a look at the disassembly of the receive input function, so you will realize that the EBP minus 8 stores this value, EBP minus C stores another value, and then there's a buffer. And then buffer might not be at the EBP minus 0x10, could be 0x20 or something. Yeah, so that depends on the buffer size. Yeah, and then the buffer is here, but our program will read up to 128 bytes. And let's take a look at what will happen if we type this kind of just 12 characters. Yeah. So we will store these values in the stack, and then if you are not familiar of the translating this kind of the character into the byte value, please refer to this kind of the ASCII code table. Yeah. So for me, it's like a 31, 61, 62, something like that. And then I believe like in few weeks later, you will also see that like character E is like 65. Yeah, you can identify that. But if you're not familiar with that, you can always go back to this kind of table. And then one easy thing is like the number 1 is starting with the 31. So 31 to 39 is a 1, 2, 3, 4, 5, 6, 7, 8, 9. And then capital A is 41, and then lower a is like a 61 in hexadecimal. Yeah. So if we type these numbers, then 1111 is a 31, 31, 31, 31. So that will be put on the buffer. But we are assuming that the current buffer size is 4. Then if we put more than 4 bytes, then CPUs are dumb. They will just run it how the compiler and the program is written. So it will just store. Yeah. So small a is 61. So 61, 61, 61, 61 is getting on there. Then it will be overriding the local variables like these. Yeah. So the one thing that you can identify is that, so if a program has a buffer overflow vulnerability, then you can change the local variable values. Then suppose you have a login interface, then you need to type username and password. And then suppose that function has is administrator variable. Then if there's a buffer overflow in typing like a username and password, then you might change that kind of variable. So like, that could be one of the way to take control of the program. But we will take a look at the more general version of the buffer overflow attack. So now we identify that the buffer overflow vulnerability give us the power to change the local variable values, but it also has the more stronger power. Yeah. And then, so if we keep putting the values, then we can also overwrite these values too. Yeah. And then for EBP and return addresses, these values we are using for maintaining how the program returns to. So like this kind of the return address is stored in here. Yeah. But if that changes, then program returns to the different point. Then let's take a look at what will happen if we type a more longer string. So this is the BBBB, and the CCCC goes to save the ESI. DDDD goes to save the EBP, and EEE goes to return the return address. So because it's linearly contiguous each other, so adjacent, so we can overwrite them all. So we can overwrite the return address, then where this program should return. This address. But this is an invalid address, so it will result in like the program crash. Then the next question might be, what if you can set that address as some of the function address? For example, get a shell function that I put for like the getting the privilege and executing the shell that to let you read the flag. So that is the main objective. So if we put a getter shell function, then at the end of the receive input, we have a function epilogue, and we will run it step by step. So it will add 54 to ESP, comes to here, and it will pop ESI. So the ESI value would be 63, 63, but we don't care. Pop EBP, so EBP value will be totally invalid, but we will not care about that. And then return. So it returns to a getter shell function, and then run the shell for you. So the main objective of the all week 2 challenges are identify the buffer overflow vulnerability. And then I didn't hide the vulnerability deep in there, deep in somewhere. So if you take a look at the receive info function, you can easily identify that there's a buffer overflow. And then the important thing you need to identify is where the buffer starts, and then calculate the distance between the return address and the buffer. And then if you put the address of the getter shell, then you can run that function and read the flag. Yeah. Any questions? Yes. So in these 4 challenges, it doesn't matter. But the challenges for level 5, 6, and 7, 8, they require you to overwrite EBP, not the return address. So in that case, you need to create a fake stack frame. So in that case, you need to take care about some of the values that you will put. But for these 5 challenges, you don't have to care about like those kind of values, because we will basically overwrite the return address and that's it. So for these 5 challenges, we'll focus on the return address. But the lecture on Wednesday, yeah. And then in that lecture, like we will learn about like the, so now we are returning to the, we are not playing with the stack frame itself. So the stack is there, but what we will learn about on Wednesday is like the stack is there, but we will create a fake stack frame and then fool the CPU to use our own data. So in that case, the values matters a lot. Yeah. So that's why these are put as a level 5, 6, 7, 8. Yeah, a little bit much more difficult than like these 5 challenges. And then again, from now on, we will have challenges in the 32-bit first, and then the equivalent challenge will be on 64-bit. Yeah. So that means, so if you can solve level 0, then you can easily solve level 1, because the only difference is the 32-bit, 64-bit. Then same thing for the level 2 and 3, but the level 4 is only for 32-bit. And then 5 and 6 are the same. 5 is for 32-bit, 6 is for 64-bit. So in that way, so once you understand one challenge, then you can solve 2. And then I set the due date for the week 2 challenges for next Monday, and there are 2 reasons. So one is like the week 2 challenges are easier than week 1. So that's the one reason. And then another reason is like in week 3 challenge set, we will learn about the writing assembly code, a so-called shell code. So right now we have a getter shell function that we can return to, but in reality, so what kind of developers would like write that kind of function there? Yeah, they might have backdoor, right? Yeah, there's no such a function that like hackers can use like that. So we need to write our own code to run it. So we will learn about the writing assembly. Yeah, and then whenever you learn about the new language, it's always easier to reading than writing. Yeah, so the writing shellcode takes a lot of time. So that's why I want to use like a shorter period of window for week 2, but having more time for week 3. Yeah, that's why. But that depends on the student's progress. Like I don't want to like to push all of you too hard. So like I will check the progress of like how you all solving like the week 2 challenges. Then like at the end of this week or something like that, I will announce if I determine to extend the deadline or. And any questions before we start the tutorials? Yes. Yes. So if we put the address of the getter shell, then it will return to the valid address where the function is. But if we put this 65, 65, 65, 65, that's not a valid address, then the CPU try to read that address, but that virtual address will not map to any kind of address. So the operating system will generate the page fault, and then so segmentation fault is a very old archaic name because in 64-bit we don't use segmentation at all. And then I believe segmentation was working before like we have a virtual memory and then those kind of thing. Yeah. So this is an old word, but what that means is like that's an invalid memory. Yeah. So to be more correctly, it happens whenever CPU try to access invalid memory address. So right now we are playing with the address, and then CPU will use that as a return address. So your wordings are also correct, right? So the CPU tries to read the return address, and that's invalid. So it happens, but in general, anytime the CPU tries to read any kind of invalid memory, yeah, it will generate the segmentation fault. And then every time like when students see the segmentation fault, they say, "Oh, this is a failure." But for the hackers, that's the opportunity. If there's a segmentation fault, then there's an opportunity that we can take control over. Yeah. So that's why I'm always telling that whenever you meet the blue screen on the Windows or kernel panic on the Linux, don't get disappointed. That's the opportunity. Yeah. All right, then let's do a little bit of tutorials. Can you see the characters on the screen? Yes, all right, yeah, all right. So if you run fetch week 2, then it will automatically like the open source, like create the directories and then symbolic links for it. And then, so we got the challenges. And then you can directly play with the program itself, but I highly recommend you to use the Python script with pawn tools to control the program, because like we need to put some of the address values in like a non-printable characters. For example, FF or FE or like the 0x1. These are not, you cannot type like those characters in keyboard. Yeah. So, but we can pass like any kind of value with the programmatically. So like they will use that. And then I create a script that you can run a get template. Yeah. And it will give you an exploit template.py for you. And then what it does is a very simple thing. It does not have much of the thing, but it just set like how you can import like a pawn tool script, and also how you can run the program, and then how you can use tmux to split the window and so on. Yeah. And then So right now, so I have got like some of the questions that the students cannot attach GDB to the program, and then that's naturally not possible because so our flag is like the set as like the you don't have any permission to read, but you need to get the permission while executing this program. And then from the ls with the color, it shows like some of the yellow mark highlighted like this, and then that means that this program has like this set GID bit. That means like while executing this program, your group ID will be changed. And then in that case, if you run this program, that's not yours. So if you execute that program, the privilege of that program goes to the that group ID. You don't have the permission. That's why you cannot attach GDB. So if that is possible, you can attach GDB and then just run whatever function. You can read the flag, so that is not the way to go. Yeah, and then to attach, but we need to attach GDB to take a look at the full, like the context of the program. And then I always tell to the students, and then one of the beautiful thing about the computer science is that for the most of other physical sciences, they are fighting against nature. Yeah, they don't know why it goes something wrong, something weird. But the good thing about the computer science is like it runs on top of the thing that human built. So we can examine every single bit and byte. So if something does not go well, then we can always open the debugger and then take a look at that and analyze that. So that's the beautiful thing. And then we will use GDB for that purpose. And to do that, you cannot attach debugger to this program, but if you copy this program, then that's yours. So it's quite weird, but just copy the program with the buffer overflow level 0 to some other name. Then you will have a program in your home directory, your working directory, but this is not highlighted as a yellow. So while running this program, yeah, you will see that the program has your privilege. So you can attach debugger for it. And then another thing is like to use the interactive debugging with the Pontools script, you need to get into Tmux. Then it will split the terminal window beautifully and then show the execution and then debugging side by side. And how you can do that is just run Tmux. Then it will get into some of the context, new terminal context. And then we will mainly working with this exploit template.py. And then right now we would like to use the debugger. So instead of running the buffer overflow level 0, I will run the buffer overflow level X, the binary program that I copied out. Yeah. And then this line is for indicating that we are in the Tmux context. So like the split whenever we attach to the GDB, it will split the window, and then on the right side, yeah, it will show the debugger. And then this is the setup for that. And then after running the program, we will attach the debugger. Works like this. And then another thing is like we need to identify the address of the gather shell function. And one way to do that is so if you type info functions after opening the binary file with the GDB, then you can see that the gather shell function is that the 8084500. Yeah. Right? Yeah. So this is the one way to identify that. But so from the exploit template, so import the Pontools, and then there's in Pontools, there's an object called ELF. And then ELF here stands for executable linkable format. And ELF is indicating that for the executable files in the Unix environment. Yeah. So it will open the binary program as an object. And then, so it reads out all the symbols, and then symbols including some of the variables, and then function names, and then if you access that, it will return some of the value. But the return value is in decimal, so if you change it as an hexadecimal, then you will see that you can easily fetch the address of some of the function with the name using this. So you can do it manually with the GDB and then some of the hand, but you can also do that automatically with the script. And I highly recommend using script, but because we will mainly play with that week 4, 5, 6. Yeah. Then and so how the pawn tool works is it will run the program and then it will communicate with the target program using pipe. And so right now our script ended here. So the program runs, but our script finishes. Then we cannot control the program correctly. So how I do it in general is there's a function called interactive. And then what it does is so with this process object, we can interact with the program with the send, receive, those kind of function to send some of the input to the program and to get the program output. But the p.interactive means that just open that to your console. So whenever you type, that goes to the program. And then if the program should have some output, then it'll be automatically printed out. So I will try to run the script. And then now you see that I can run it again. You can see that on the left side, it runs the program. On the right side, it runs the debugger. Yeah. So you can take a look at the context and then others from here. This might be a bit better. Yeah. And then to control the debugger correctly, and then this is the disassembly of the main function. And then we know that internally it will call the receive input function. And then from here, we know that there are lots of printf, but from the app gets, it will wait for our input. Yeah. And then it will do some of the check. And then if the values are something different than this, then it will run get a shell function or return. So the one way to solve this challenge is that you can match the condition at here to let them run get a shell function. But I will demonstrate the way that you can solve a level 2 and 3 to solve the same challenge, to solve the level 0 and 1. Yeah. So suppose we change the return address, then we are hoping that the return instruction to fetch that value. So what we will follow afterward is on the debugger is we can set the breakpoint at the return address, return instruction, and take a look at how the stack is formulated and then how it works. And to do that, I will set the breakpoint at 2 points. So one is the right after we send that input. So right after the app gets executed, and then the return instruction. So I will set the breakpoints at this address, and then this address. So I'll just copy these 2 addresses. Then when you attach GDB, you can add some of the GDB command here. Yeah. I have not tried like a multi-line here, but let's try. I'm not sure this works or not. And then oh, it works. Yeah. So let me explain the how it works. So right now, our script run the program and attach GDB. Yeah. And then our program will call fgets function. And then internally, fgets function calls a system call definitely the read function, yeah, to read the user's input. But that's out of the program's context, and then that's on the operating system side. That's why our program stopped at the kernel vsyscall. Yeah. So you can regard this as like the program tried to access the operating system to get the user input. So our debugger knows that, and then debugger stops whenever it goes out of context. So that's where it has been stopped. So what we will do is just to continue. The reason is like we want to focus on not the operating system side, just on the program side. So if you run continue, and then it keeps waiting for our input. But on the left side, I will just type some AAAA, some of the input like this. Yeah. Then the next breakpoint is like right after running the fgets function. So it's stopped at here. Yeah. And then we set the 2 breakpoints, and this is the one. Then if you run continue again on the debugger, then it will stop at the return instruction of that function. That's how you can set like the where to watch for the execution. And then the next thing is that we will identify the length of the buffer to overwrite the return address. And to do that, let's take a look at the disassembly of the receive input. Yeah. And then from here, so this is the fgets function. And then fgets runs with the buffer size and then file stream. Then we can see that what is the first argument, second argument, third argument of the fgets. And then this is the third argument, 0x8 ESP. 0x4 ESP is the second argument. Then we can know that size is 0x80, which is 128 in bytes. And then the first argument, the buffer, is coming from EDX. And then that is EBP minus 0x20. Yeah. And then please recall that the stack frame, yeah, at the point of the EBP, we store saved EBP, and then EBP plus 4 will always store the return address. So to overwrite the return address, so our buffer is EBP minus 0x20. So we need to overwrite 0x20 bytes, and then 4 more bytes for the saved EBP, and then return address. So 0x20 is 32 bytes. So we need to overwrite 36 bytes, and then the return address. Then let's check how that works. I don't know why. It I'll hit the debugger and then run it again. So 10 bytes, 20 bytes, 30 bytes, 36 bytes, and then I will put AAAA. So now the debugger is at the point after running the apt-gets. Then I'll print out the stack. Can you identify where our inputs are? These are our inputs. So number 1 is 31. And then because Intel architecture uses a little endian, yeah, 1, 2, 3, 4 comes like the 31, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 0, something like this. Yeah. So that these are our inputs. And then we can also see that this 4 on 4 on 4 on 4 on is 4 overriding the return address that we hope. Then let's check whether it really overwrote return address. And then to do that, I will check value around EBP. So right at the address of the EBP, it stores a saved EBP. And then the next value is the return address. But that's 4 on 4 on 4 on 1. Yeah. So the return address has been successfully overwritten. Then I will do continue, stop at the return instruction. Then the PON-DBG debugging script, it will show the stack frame like this. So that you can regard this kind of the stack values as the diagram that you have seen on the slides, but it's upside down. Yeah. So right at the ESP, we have the value as AAAA, as we typed it here. Yeah. So receive input will return to this address. So if I move forward with the next instruction, then it says invalid address, because that is definitely an invalid address, right? Yeah. And then our proposed objective is like running the getter shell function. So let's put the address of the getter shell at there. And then now we will use the Palm Tools API to interact with the program. So to send the input to the program, we can use the p.send because now the process is p. Yeah. And then what we will do is we have buffer size 0x20, and then it includes like local variables too. And then save the EVP will be there, and then return address will be there. So we override 0x20 and then 4 bytes. And then if we add up those, 36. So we need to prepare attack payload as 36 character, and then address of the getter shell. And using this ELF object, you can easily get the address of the getter shell, but that's the integer value. You need to change it to the byte stream. And to change 4-byte value, integer value to the byte stream, you can use the function called p32. Yeah. Something like this. Then it will change the hexadecimal address into the little endian bytes. Yeah. Then you can put on the program. And make sure you need to use a p32 for 32-bit challenge and the p64 for the 64-bit challenge. Yeah. Then this will be our attack payload. And then I will print the payload and send it to the program. Then I will run it. So likewise, it stopped at the system call. We'll just continue. My bad. Because you use fgets, right? And then that expects the new line to stop the reading the data. So that I will use send line. So the difference between the send and send line is like a send line just add a new line, or it's actually equivalent to do something like this. Yeah, adding the new line at the end. So I will continue. Then it stopped at right after running the fgets. Then let's check. The stack frame. So the starting from ESP, so we will see that inputs because I just put the A multiplied 36. And then at the end, we can see the address of the getter shell here. So if I continue, then now the return instruction will fetch the return address from the getter shell. Yeah. Then if I run next instruction, that it will get to the getter shell function and it will run that for you. But in this case, it says like the spawning a privileged shell, but it does not work well. The reason is like we are in the debugger. Yeah. So it's actually the same group ID that I have. So I recommend using debugger to get to the point that you can successfully control everything. Yeah. After you identify that your exploit script works, then what you can do is, so I previously used the debugger, but now I do not want to use the debugger. Now I know how to solve it. Then we don't need these kind of the GDB that attach. Then after changing these few lines, then the script will directly play with the target binary program. Then let's run it. So the same thing, and then it successfully ran a get shell function. And if you type ID, then you can get the group ID. Any questions on using like a GDB, TMUX, and this kind of tool? So maybe you are curious about like what kind of APIs are available for Pwn tools. So we do have a link on our course website about the Pwn tools document, or just search Pwn tools documents, then you can have a great website describing all the APIs. Yeah. But we will mainly use like the process, attach, and ELF, and then send, receive. These are the main thing that we will use, and then we will learn the required thing as the class goes on. Any questions? Then let's do the similar thing on the 64-bit. So this is a 64-bit challenge, and then the different thing you will immediately see is that the address is 8 bytes. Yeah. So it will have a lot of zeros if it has like the low address. Yeah. And then you can regard like the only change is like that they will use registers for passing arguments. Yeah. And then we can get into the receive input function, and we will mainly focus on the fgets function, and then where it puts our input, and then what is the distance between the return address to the buffer. So for this fgets function, so the argument passing order is RDI, RSI, RDX, CX, and on. So the first argument is the buffer, and the first argument is coming from the RDI. So we can know that our buffer is at the RBP minus 0x30. Yeah. But the same thing, RBP points to the saved RBP. So that's why in 32-bit exploit, we add 4, right? But in 64-bit, we need to add 8. because each of the word address are all 8 bytes in 64-bit. So what we need to do is 0x30 is 48 bytes, right? So we need to fill 48 bytes and then 8 more bytes to fill up the saved RBP and then return address. So from the basic calculation, we need to put 56 bytes and then the return address. And then I told you that the buffer flow level 0 will be really, it's identical, but the architecture is different. So what I will do is I will copy the exploit template to here. Then now we will play with the debugger first. Now we'll enable that. Then fix a little bit. Later we will run buffer flow level 1. But for that to use the debugger, you need to copy the binary program that has no sticky bits like this. And then another thing is, so we need to set the breakpoint similarly, but the address is different. So we set the 2 breakpoints for the level 0. That's right after the app gets, and then at the return address, return instruction. So we will set the breakpoints at this address, right after the app gets, and then this address. So I will copy these 2 and into the exploit script. Then like this. And then we know that the buffer size was at the EBP minus 0x30, so we need to fill 0x30 bytes. And then save the RBP will take the 8 bytes. So we need to fill up 56 bytes. And then just use something like this. And then in 64-bit challenge, you need to change the get a shell function address into the 8-byte binary byte stream. And then that's it. And let's see how it works. Why it doesn't work? That runs, right? It's too slow. That's why. Right. So we're at here. Then same thing. If we do continue, then it will stop at the right at the after running the fgets function, and then we will check RSP values, and then we can see that our inputs are here, and then so RBP minus 0x30 was like where our buffer is, and then we print some of the values, then we can see that we put our input right at the buffer, and then overwrite all the bytes, and then at the end, it also overwrites the return address. And then another thing you can easily use like this is 8 bytes, and then 16 bytes are 10 in hexadecimal. So we know that the buffer size is 30. Then we need to have like 3 lines of the 16 bytes. And then this is the position of this 8 RBP. And then this is the return address. And if you continue, then it will stop at the receive input. Then it will see the get a shell function. Then it will continue to run it. And if I do continue, then there's a spawn the privilege shell. But right now we are in the debugging context, so that you cannot get the GID permission. So after you successfully run the getter shell function, try to fix the script as running the real target binary program. Then slow. Then you can get the GID permission. So right now, I actually demonstrate how you can solve a level 2 and 3 because the 0 and 1 is much easier. So if you just match the local variables, then you can pass it. Yeah. So any questions in demonstrating this demonstration of solving these 2 challenges? So I believe like the 0, 1, 2, 3 are very straightforward. So if you can change the return address, then the problem solved. But I want to discuss a little bit about the level 4. Then what it does is that, so you need to change the values to this one. And then also it stores the return address. And then at the end of the return, it will check if the return address has been changed or not. Yeah. So basically what it does is like we have a stack frame, and then there's a return address. And then so in the receive input function, so actually these parts are, so EBP plus 4 is the return address. So at the EBP, we have a saved EBP. EBP plus 4 is the return address. And then what it does is like it will move the return address value to here, and then store that to in this address. So when it calls a receive input function, we will get the return address and then store somewhere else. Yeah. And then at the end, what it will do is it will, where's the comparison instruction? Yeah. So this variable is the stored return address, and then it will fetch the current return address and then compare that at the end. So if the return address has been changed than the original return address, it will kill the program. Yeah. That's the thing. So overriding the return address of the current stack frame will never work. So there's some of the students are lost, yeah, and don't know how to solve it. But please think out of box. So we have a main and input function, receive input, right? So that we cannot change the return address of the receive input, but we can change the return address of the main function. Yeah. That's the key to solve the level 4. So please, yeah, keep that in mind. Yeah. So And then like the level 4 is the practice of like the avoiding some of the very naive defense. So like the just blocking the operating the return address of the vulnerable function would not be the solution to the defeating the buffer overflow vulnerability. Any questions for the materials for today? Yeah, I know that around half of the students have already finished these challenges. Yeah, but yeah, I was thinking about releasing one interesting extra credit challenge. Yeah, for this week, so to make the fast goers like the have more fun about that. Yeah. All right, then. So let's start in class exercise, and then ask whatever questions you have. Yeah. Then you can also free to leave. Yeah, if you already finished all the challenges. Yeah.